So, and also she will share some tutorials sheets with you. And like I said, I would like these sessions to be interactive, because otherwise I have no idea what your response is. So I'll also urge all of you to take out your notebooks and have a pen ready, so that if I stop and ask you a question, you can compute. So please do that. So, cosmic dawn. So you have already heard a few lectures on H1 signal in cosmology, what is called 21 centimeter cosmology these days. And one important era of this signal is what's called cosmic dawn. And I will just show it to you through a picture first before I go to my course plan. So this is a picture, and you must have seen it many times, maybe during the school itself. This is the Big Bang. It's a very long time ago. We don't really know when. Then there is this era during which the universe is completely ionized. It's filled with ionized
Shiv, you can go full screen so that we can
I go full screen?
better. Yeah, I think it will be better.
If I can go, I'll just see if I can go full screen here. I am trying to.
So F5 in Linux.
F5?
I guess F5 will work in Linux. Are you using Mac?
Yeah. Yeah, it's working. Yeah, so I don't have to worry about. Okay, so this is, so now I'm full screen, right?
Yes.
So this is how far it'll go, but I'm sure everybody, they're just staring at their screen so they can see it, right? So here is a schematic of what we are dealing with here. Big Bang, and then for a fair amount of time, the universe is filled with ionized plasma. And at some point, a time when the universe was 300,000 years old, and we'll discuss this phase in detail during this lecture, the universe becomes neutral. All the hydrogen, universe is dominated by hydrogen, recombines to form neutral atoms. And so this blue shades here is when the universe is neutral, and it says opaque here. Don't worry about it. It is transparent to some photons. This is what is called the starting of dark ages. The universe becomes, these are dark ages. We have fair amount of information when the universe was about 300,000 years old. In fact, our best information about the universe comes from this era. This era, when the universe was around 300,000 years old. Then the dark ages begin. By dark ages, we really here mean that we do not have much information from these ages. And you'll see the reason why. Then this era ends when the universe is close to 500 million years old. And this is when the first structures in the universe form, galaxies and quasars, and of course, subgalactic structures, most of them in the beginning, they form and they start shining light into the medium surrounding them. And this causes very many things, and you would see very many things, but one of the things it causes, it ionizes the medium around. So as it ionizes the medium around, more and more such structures form as time elapses, from roughly 500 million years to 1 billion. And these structures, these ionized structures, they grow. They are called Stromer-Green sphere. They are or H2 regions. And finally, this era finishes. It finishes around 1 billion years. The cosmic renaissance, the cold dark ages end. There's a very European way of looking at it, because dark ages and renaissance, these are two words like which are used, but you can use your own words if you feel like. So around 1 billion years after the formation of the universe, or whatever, since the Big Bang, reionization is complete. The universe becomes transparent again to some kind of photons. Then galaxies form and they evolve, and the universe is almost fully ionized subsequent to this era, all the way to now. And that's how it is. And that's how we understand it. And we'll touch upon only a brief part of this history of the universe. My focus would be between 300,000 to 500 million. Later on, Tirth is going to talk about epoch of reionization, which is roughly when these ionized structures start forming. So I will be talking about ionized structure and their formation, but I will end somewhere just after 500 million years. I'm not going to go all the way to 1 billion years. I'm going to stop. So focus would be between what are called dark ages and what we can see in dark ages, and what is called the era of cosmic dawn, when these first structures just start forming. What kind of information can be ascertained from studying this epoch? So it is very early phases of epoch of reionization, which is what is generally referred to as cosmic dawn. So here is my course plan. Wait a second. Here it is. So my course plan is to, like I said, I'll start around 300,000 years old when the universe was around 300,000 years old. And I have good reasons to do that, and you'll appreciate them as the lecture goes on. So first I'll study ionization history of the universe and pay special focus to the process of recombination of primeval plasma. Why it is so important, you will see. Then I will go on to discuss thermal history of the universe. What is the thermal history of the universe? When I say thermal history, I really mean here a history, a separate history in some way of particles and photons. That's why the main focus would be on post-recombination era and thermal decoupling. Then I will discuss what these first do, what kind of impact it has on mixing hyperfine levels in hydrogen. And I'll discuss relevant physical processes. You already have come across some of these. So there will be some overlap with something else you are hearing, and that is perfectly good, because like if you hear similar things from more than one teacher, things tend to get set in one's mind. Then I'll talk about radiative transfer again. Briefly, I'll be brief about many of these things. And what kind of signal do we expect? The whole idea of this set of lectures, as you would have and know already, we are looking at the H1 signal. We are looking at the hyperfine line of H1. That's what we are really studying here. I'm not going to discuss anything else but the hyperfine line from neutral hydrogen in these lectures. So the radiative transfer, the H1 signal from pre-dawn and cosmic dawn era, I will discuss in some detail. One reason for this course plan is to discuss what's called edges result, and edges result and its many variants are already out and it's still being discussed. It's a result from just a few years ago. And this was the first indication. It's an observational result. We never really expected to be able to get any information about cosmic dawn, but it was very surprising. We did get some information about cosmic dawn. And as it turns out, the information, if correct, uh, is open to multiple interpretation, and I'll discuss them during these lectures. And then the future prospects. One important thing about this era and what I have done in this view graph, I have just put in some number and I told you take out your notebooks and pen. You can note down these numbers and you can of course verify them yourself. Is that a part of the study is fairly precise. It deals with what we call precision cosmology, and that's why I'm talking about recombination and thermal history in some detail, because some of those things are connected to the best observables we know in cosmology. That's on one hand. And on the other hand, we deal with a whole range of other models, which are fairly imprecise, but will be fixed by observations, of course. As observations come, and they are already observations, and observation close to redshift 10, the epoch of reionization, will be discussed in some detail later on. I'll not touch upon them. So it's actually a mix of two things. On the one hand, something fairly precise, something we can't play around with without violating the best bounds that we have seen in cosmology. And on the other hand, something fairly uncertain, which we can only get not from theory so much, but from an observational perspective, from an observation. These are cosmological parameters that I'll be using in this lecture and also later on, and you may have come across already. First is, the value of omega b h squared, the baryon content of the universe, the total matter content of the universe, the value of Hubble's constant, how you compute expansion rates at high redshifts from these quantities. And I will use things like Hubble time scale or scale, Hubble scale interchangeably. One of them is a time, the other is a distance. And that is how they are defined. I have just written them here. Number density of baryons, what we expect the number density of baryons to be based on CMB observation. That's the first line of this view graph. Then I'll be using in this lecture recombination coefficient to the first hydrogen excited state. And that I've listed here, and it has some usefulness here. I'll discuss ionization cross-section of threshold for hydrogen, something I'm going to use today. And I'll expect you to use it too. I'll stop and ask you to compute it. And Lyman alpha cross-section. at temperature of around 1000 degrees, like what kind of difficult cross sections we expect of these processes. So what I would like you to do, as I said right in the beginning, you can note down these numbers now, and I can expect you to give me some answers later during the lecture. Okay, so let's move to the first topic, ionization and thermal history of the universe. So, as you know, all of you know, and I expect all of you know, I mean, Janaki has put out some, has shared with you through Slack some notes already, or she's going to do it very shortly.
Uh, yes, sir. I will be doing that in an hour or so.
All right, so she hasn't done that yet, but she will do it in an hour or so. So that will give you, so there are very many details, some background also, but you have learned some background during this course also. So the universe, as you know, is expanding. We know that from observation, and we expect it was expanding in the past also, in fact, faster than now. And during the expansion of the universe, we can, and I'll come back to this point, the temperature of the universe falls as 1 over A. And when we say temperature, here I mean a temperature, a common temperature between photons and matter. So let me just say what matter is when I say matter, because I'm going to use later on Tm, which is referred to matter temperature, and T, CMB, which will refer to temperature of CMB. But in these view graphs, I'm using something called T, which is a common temperature of all of these. So look at, let's see how many different species we really have in the universe. So early in the universe, when let's say redshift of 10 power 5, just before that, or whatever, up to redshift of 10 power 9 really, we have hydrogen, which is around by mass 75%, by number all more than 90%, 92% of all the particles are hydrogen. Remaining 8% are mostly helium actually. So these are two. And then hydrogen, like I said, is ionized. So there are electrons and there are protons, right? So electrons, protons, helium, nuclei, different stages of helium, and photons. This is what the universe is during the early phase. So when I say hydrogen recombination, I am going to focus on hydrogen. So what happens as the universe expands is the common temperature of all of these species falls as 1 over A. And when it falls, the universe is fully ionized when the temperature is high, but when this temperature falls below roughly the ionization energy of hydrogen. So the process of recombination is a two-way process. Electrons plus protons form a hydrogen atom and emit a photon. But it can go the reverse way also. If other photons and particles in the universe have high enough energy, they are not going to let this process move forward. Right? So you are not going to form a lot of neutral hydrogen when there are a lot of energetic particles in the universe. When the temperature falls below 13.6 electron volts, at that time, we have energetically a situation where hydrogen can start to recombine, or there will be a preference later on for neutral hydrogen over ionized hydrogen. I have written here in bracket the helium. One may ask, what about helium? Helium has larger ionization energy. 24.6, it has two ionization stages, neutral 24.6 and singly ionized 54.4. They recombine a bit before hydrogen. And I'm not going to
I ha-
on this. Go on,
I
please.
have a doubt. Are
Yes,
we
please.
actually ignoring our neutrinos?
Sorry,
So
say
you
it again.
haven't like see you said we have electron, proton, hydrogen, helium,
Mhm.
photon. So don't we have neutrinos?
Yes, the neutrinos actually are not in thermal equilibrium with this thermal bath. Neutrinos were in thermal equilibrium with this bath before a temperature of roughly 1 million electron volt. That is a redshift of around 10 per 10. So they were coupled to this bath at that temperature. You see, because neutrinos coupled to the rest of the matter through weak interaction. And the rate of weak interaction is much smaller than electromagnetic interaction. So I left out neutrinos because neutrinos are separately, the phase space distribution of neutrinos is separately conserved, but they are not a part of this bath, not at the energies and redshifts I'm talking about. Does it answer your question?
Yes, yes. Thank you, sir.
Yeah, good. So when the temperature starts to fall below, below ionization energy of hydrogen, I've written 10 power 4, actually it's higher than that. I wanted to compute that number. This is an exercise of converting temperature into electron volts and vice versa, and it's always a good exercise. Everybody who works in this area should know these numbers. So compute this number, right? Make a note and compute this number. Very simple exercise. Okay, so how do we follow this process? Hydrogen begins to recombine when it's energetically favorable for it to recombine. The temperature is falling below 13.6 electron volt. What equation do we use? How do we actually compute the evolution of the ionization state of the universe? In fact, the equation we use, and famous equation of Saha, it's called ionization equation. I have written this ionization equation for hydrogen, and I should have said hydrogen in its ground state, because this equation is not valid for hydrogen in its excited state, but for ground state. I mean, this is an equation that Janki will discuss with you in some detail, and you should know this equation well. Ionization formula, as you can see, relates the number of electrons. So Ne is the number of electrons or protons. Universe, notice, is neutral. So number of electrons is the same as number of protons plus the helium nuclei. I'm not bothering about helium nuclei. I'm just assuming they exist and they are in small numbers. And they do not make any difference to this exercise. So I've just neglected them. So Ne is the number of free electrons, and their number for all intent and purposes is the same as the number of protons. Even the number of electrons is a little more because of helium. Doesn't matter. NH is the number density of neutral hydrogen. And this gives you a relation between the two. When you go out of equilibrium, when you are in equilibrium, in thermal equilibrium. And if you notice, this tells you that when the temperature of the universe falls well below the ionization, the ionization energy, then Ne falls exponentially in this case. And you can see it's a fairly straightforward thing, that Ne will fall exponentially and keep falling, even though, because NH plus Ne is equal to the baryon density, you'll have to solve this equation more carefully, right? Because NH is not independent of Ne, right? NH is just NB minus Ne. So, but it is clear that if all the processes were in equilibrium, and I will actually quantify this term. What do I mean by equilibrium? Then the number density of electrons when the temperature of the universe falls well below 13.6 electron volt should exponentially drop. However, this equation, even though it is actually a good equation for initial condition in the universe, and it is actually a good condition for initial condition, it doesn't work when the recombination process starts. And that is why we need to study the recombination process a little more carefully, and you will see it will have a bearing on what the observable is. So we now go from this equation, which is a fairly simple equation, it can be derived and easily solved, to a more complicated set of differential equations. In fact, there are two. I'll discuss one in the next view graph and one a little later. Here you go. So how does the process of recombination work? Okay, I'm sorry. I think I'll just go like this. Okay. So let's first look at hydrogen levels before we understand the process of recombination. I just go forward and then go back. Okay, fine, it's working. So if you notice the hydrogen atom, these are the principal states of hydrogen, which I'm sure all of you have studied in undergrad days. So there is a ground state which has an energy of minus 13.6. You know this. It's negative because it's bound. Then there is a first excited state, and because I'm going to discuss first excited state, that's why I've shown you this. It also is negative because it's still bound, and the energy is minus 3.4 electron volt. Difference between these two is almost 10.2 electron volt, and it's called the Lyman alpha transition, as you know. And then there are higher and higher excited states. You can see going all the way to the continuum. So here in this view graph, you have n equal to 2, n equal to 3, n equal to 4, n equal to 5, n equal to 6, and n equal to 7. When recombination happens, the first question, of course, is to which level does the electron come to? So electron and protons, they combine. Question is, to which level? Do they come to n equal to 1, n equal to 2, n equal to 3, n equal to 4? Well, the answer to that question is with some probability to all levels. They can actually combine to every level. There is a certain probability for them to combine to any level at all, even though the probability decreases quite sharply when the recombination happens to an excited state. So the process of recombination is essentially driven by n equal to 1 and n equal to 2. In most cases, there are cases when n equal to 3 and n equal to 4 will dominate. N equal to 3 plays an important role in some parts of interstellar medium, but I'm not going to say much more about that. Our entire focus during this lecture would be n equal to 1 and n equal to 2. So this is the process of recombination. Recombination to ground state. What happens when you recombine to ground state? You produce a photon. Remember, electrons plus proton, if they recombine, they produce a hydrogen atom and they produce a photon. But you see, you have gone to a negative energy state of minus 13.6. An electron has lost a bit of its kinetic energy in recombining with hydrogen atom if you conserve energy and momentum. So the photon that you produce as from this process has an energy more than the ionization energy of hydrogen. It should be clear to you that it always will have energy which is larger than the ionization energy of the hydrogen. And this is exercise 1 for you. Based on the numbers I showed, show that this photon causes another ionization nearby, or its mean free path is much smaller than the Hubble scale. In fact, I shouldn't have said it. You should, after we are done with this, you should ask yourself what does it mean for a photon to escape the medium. So I will return to this point if I have time later during this lecture, or Janki might discuss with you later during a tutorial session. So this means recombination to ground state doesn't work. It doesn't really recombine. You can come to ground state, but you'll produce a photon which can ionize the medium, and it does ionize the medium. It doesn't travel very far before it ionizes the medium. What is the meaning of traveling very far and ionizing another medium? Meaning of this we'll come back to maybe later during this lecture or during the tutorial. Point, recombination to ground state doesn't work. Okay, how does the recombination happen then? You can recombine to the first excited state. I showed you those states in the last view graph. That view graph did not show you the breakup of the first excited state, but the first excited state breaks up into two states, two kind of state. One is a 2s state and one is a 2p state. And again, you probably might recall it from your undergrad days, even though you may never recall it. I never recalled it unless I studied it actually. You always forget that there are two states, and one is a 2s state and one is a 2p state. And they behave very differently. And they behave very differently because a photon can go from first ground state to a 2p state. It cannot go to 2s state actually. Because you see, 1s to 2s transition is a strictly forbidden transition. Why? Because angular momentum is not conserved here. Right? The angular momentum has to change by a unit, and it doesn't change here. But 2s does decay. But it's a 2-photon process, and it's a very slow process. So if you notice, if you recombine to 2p state, you go to a ground state producing a Lyman alpha photon, and the rate of production of this is around 10 power 8 per second. In fact, it's 6 into 10 power 8 per second. I've just written 10 power 8. But the 2s state, if it comes to 2s state, it decays far more slowly, only 8 per second. It's an extremely slow decay process. However, there is another thing that needs to be kept in mind here. The Lyman alpha photon, and again, now you'll have to go back to the numbers I gave you right in the beginning. I gave you the cross section for Lyman alpha, right? So if you use typical numbers there, you would find that even if the neutral fraction of the universe is extremely tiny, Lyman alpha photon, you go to the ground state, but it gets captured, it again scatters back to the excited state. So it keeps scattering back and forth, back and forth, back and forth. What have you gained? You have gained nothing. You haven't actually made a transition from an ionized state to a neutral state because this Lyman alpha photon has prevented you from doing that. So it scatters multiple times. But what happens during the scattering? I've written here actually, before the expansion moves it out of resonance. So what happens is, just imagine a photon which is going from ground state to excited state, go back again, and it has a certain mean free path. And the mean free path you can actually compute from the numbers I've given you. So, but expanding universe does something else to you. When a photon travels, it redshifts. Photon can travel in whichever direction, but it always redshifts in an isotropic when the expansion is in 3 dimension. So there is no way, it's not like a 2-dimensional picture, it's a 3-dimensional picture. So wherever the photon goes, whichever direction it moves in, it actually redshifts. So a photon can multiply scatter, but it keeps redshifting. The resonance, and I'll show you the resonance of Lyman alpha is very narrow. It moves out of the resonance after a while. So once it moves out of the resonance, that photon cannot now get captured by the ground state. So you complete one transition by that. So you might already notice it's a pretty complicated process. 2s and 2p states, they play a very important role and they behave very differently. You may ask, why not recombination to other excited state? I already said, if you go to an excited state, there is always a probability that you can come to 2p or 2s state. And this is precisely what happens after few scattering of those photons. And the rate of recombination to this state is also small. So for all intent and purposes, we deal with only first excited state. We do not worry so much about other excited states, even though we can deal with them. Now people have actually worked it out. But what I'm going to show you is precise to almost 0.5%. So people have dealt with multiple levels. Now hundreds of levels people have studied this recombination process. But what I'm going to tell you, which is a pretty order of magnitude calculation done by Peebles and Kurt Soniev and Zeldovich way back in 1960s, works. So here it is. So this I have actually taken from Peebles' Principles of Physical Cosmology, and I've given you the page number. So you can actually go and look up that book. For the derivation of equation 2, I will not derive it here. The derivation would have taken me a little longer, even though it's quite instructive, the derivation of this. So this gives you the time development of the ionized content of the universe. And it's a differential equation. There is a C that is sitting here, and this C is a complicated function of the decay rate of the 2s state and the destruction rate of the 2s state. So I have actually not even given the form of it. If you notice, there is this expression in the bracket. If you equate the two, you'll get ionization formula. So it actually justifies what I said before about ionization formula. In that case, the left-hand side goes to 0. That doesn't mean that these two, that doesn't mean the electron fraction, like the ionized fraction, stops changing. But it changes in accordance with these two terms, the first and the second terms being equal on the right-hand side. And this happens very early in the universe, actually. Very early in the universe, this indeed holds. One process, which the first process is square of the number density. So that's pretty large in the early times. And this process, the second process, the temperature is high, so the exponential factor is not suppressed. It's almost unity. So like I said, it's a reasonable initial condition. But by the time the recombination starts, and it's a little delayed, it happens not at 10 power 4, but closer to 1000. Both of these terms are somewhat larger than expansion rate, but not much larger than it. So you have to solve this differential equation. You cannot use the ionization formula. And you would notice the electron fraction, the ionized fraction doesn't change, it doesn't go exponentially. It's a very important fact actually in this entire narrative. So again, I've given you alpha is the recombination coefficient. I've given you the value of this. Beta is the thermally average rate of destruction of the 2s state. And you can actually see it in Peebles' book and actually derive it yourself, because this actually derived from having thermal equilibrium in the way of Saha equation. That's how it is derived actually. It's a very neat application of what's called Einstein E and B coefficient. If you know one process, you can calculate the inverse process, so long as you're in thermal equilibrium. You are in thermal equilibrium as far as the photons and electrons, their free motion is concerned, but you're not in thermal equilibrium as far as the hydrogen atom is concerned. And that's exactly what we are studying. The different states, they are not in thermal equilibrium, right? And that's precisely the point. If they were in thermal equilibrium, we would have used the ionization formula. We cannot, because they are not. So initially, what happens is the second term on the right-hand side is small, and but it builds because it's proportional to the NH. I had called it NH in the previous view graph. This is the population of the 1s state in the ground state. So it rises, it becomes important. Ionization fraction keeps changing, and it changes to around 10 power minus 2 by redshift of 800. I'll show you a figure, so do not worry about these numbers. Point is, in the solution of equation 2, initially, very early in the universe, the right-hand side vanishes. then this term is really small. Recombination dominates. C by redshift of 500 is of the order of unity. And the equation 2, the second term on the equation 2 was exponentially suppressed, so it is gone. So the only relevant term is the recombination term. You notice it's not a simple picture at all. If ionization formula was to hold, those two terms will be on the same order, but they are not. Expansion of the universe has caused two things. It has made the temperature drop, which has exponentially suppressed one term, and it has also made the density drop, right? Which means all the processes are slower than they would have been. So at around redshift of 500, we have a much simpler system. We cannot destroy neutral hydrogen because we do not have enough energy to destroy neutral hydrogen. But we can continue to recombine, but at a slower and slower rate. And here is the computation of recombination rate versus expansion rate. And again, I have used the expansion rate as given in the first view graph that I showed on numbers. And this can readily be computed. It can be computed very easily because it's proportional to alpha, whose values I know as a function of temperature. Xe is something that I do not know, which I'm going to solve from this. N is the number of baryons, T is the time, which is what's called the Hubble time, or with the inverse of the Hubble expansion rate. This recombination process, so you see in the past, because it's proportional to NB, this was larger than unity. Recombination rate was more than the expansion rate. But as time passes, recombination rate drops below expansion rate, but it remains comparable to that. So when the second term on equation 4 becomes on the order of unity, that is the time the recombination rate and the expansion rate become on the same order. They are large before. First you're dominated by recombination, then the expansion rate will take over. And the value of Xc to which it freezes is that value. So recombination process freezes when the two rates become equal. Or the right hand side of 4, equation 4, the second term is on the order of unity. You can solve for it and compute what the value of Xe is. And the value of Xe at redshift of 100 is around 10 power minus 4. So let me say what I've said so far. We wrote down an equation, we actually analyzed what those terms were, but we actually computed them numerically, right? Showed one term becomes less important over a period of time. The only term that dominates is the recombination part. Even that terms become subdominant to expansion rate at some point. And there is a freeze out. And the freeze out happens at an ionization rate of 10 power minus 4. At this point, you might be wondering, is 10 to the power minus 4 really important or it is not important? It is very important, and that's what you'll see when we study the thermal history. Here I show you actually a figure of recombination of permeable plasma. So if you notice in this figure, you start, redshift you can see it decreases as you go from right to left in this picture. And this is the ionized fraction. Ionized fraction is initially unity when you are much more than the redshift of 1000. So it's not 10 to the power 4, it's close to 1000 when the recombination actually happens. Around a redshift of 1000 or so, the ionized fraction starts falling. It keeps falling, but it doesn't fall exponentially ever if you look at this carefully. Okay, I shouldn't say ever. For a short while after 1000, it does fall exponentially. So ionization formula, more or less valid. But then it tapers off and it actually flattens out. If you notice, it tapers off and it flattens out. It keeps slowly decreasing all throughout, and it has to because the recombination rate, even though it is smaller than the expansion rate, is still happening. Recombination is happening at some rate. So this is how a typical plot looks. It's not an exponential plot. It decreases, not as sharply. I should have put an exponential plot on it to show you that it is not an exponent. It's an exponent probably just when it happens, and then exponent will deviate from this curve. It is flattening and finally flattens out and gives you an ionized fraction of around 10 power minus 4. You are seeing other curves in this figure. And these are figures like that. This is from a paper of mine. So these are figures like we were studying some models in which the universe get ionized very early on, actually, close to a redshift of 5 to 600. And these are those models. So those models are not relevant for our discussion. I'll not say anything more than that. what is relevant for our discussion is the solid line. So that is how recombination to of the primordial plasma happens. The universe becomes neutral, nearly neutral, from fully ionized between a redshift of 1000 roughly to a redshift of few hundred, you can say. I mean, it's up to you what you want to say. What is relevant for us is the fact that the residual fraction of ionized fraction is not very, very small. It's just 1 part in 10 power 4 and will play an important role in what we'll study next. Now I'll stop and I'll take your questions if you have anything on this part. And then I'll go on to the thermal history of the universe. So I'll stop now for your questions.
Hi, Shiv.
Go on.
Yeah, so this is Kanan. So this recombination rate at redshift around 10, the rate that is available in literature, are they correct, or they need some modification?
Yeah, there are modifications. In fact, I think from what my figure, the one I've used in my figure itself is probably somewhat incorrect in that paper. And the reason is the experimental data for some of these things is still lacking actually. Okay.
Right.
At 10 power 4 or 5, we actually do understand recombination process at some temperature. So there are multiple fits to this. But they are not off by more than 20%. But change of 20% can give you roughly a factor of 2 in residual ionized fraction.
Right.
So, for instance, I have more figures after this. I have just picked it from one of my early, this is a paper I wrote in 2005, actually, so long ago. When I produce figures now, they change a little actually, because I'm using a different fit to the recombination coefficient.
Right.
So even the recombination coefficient I have given you, that is actually what is quoted in people's book.
Right.
But if you look at recombination, generally we tend to use rates in right now in cosmology. Most of us go back to a paper of Chen, which is 1992, where all of these rates are listed from comprehensive literature. Okay. They differ a little actually.
So how those recombination rates are calculated? Is it atomic physics calculation, or how they are actually calculated?
So you see, the recombination rates are computed from what are called Milne relations. Okay.
Right.
So Milne relations, so Rybicki and Lightman has a long discussion on Milne relations. So in Milne relation, we first compute the rate of ionization, photoionization. After we compute the rate of photoionization, and that can be computed quantum mechanically, Rybicki and Lightman doesn't give you the detailed quantum mechanical calculation. You'll have to go and look at either Landau-Lifshitz quantum mechanics or one or two quantum mechanics of 1 and 2 electron system by Bethe and Salpeter. They give you details of how those ionization cross sections are computed. Once you know ionization cross section and you know Einstein A and B coefficient, that if you know the process, you know the inverse of that, you can actually compute the recombination coefficient and do thermal averaging over them. Problem is, there is a bit of uncertainty of how you actually average over higher excited states. Right. You have to take that into account. So there are many calculations in quantum mechanics which have been done, but some level of uncertainty remain. So that is where this uncertainty stems from. So if anybody is using recombination coefficient, if I use recombination coefficient today, I just go back to the paper of Chen in 1992 and just use it, and I quote it, I cite it. But I have seen that some of these rates are uncertain and it has to be kept in mind, right?
Right.
Even though, I mean, but most of the uncertainty comes from integrating over the partition function for higher excited states. The degeneracy changes quite dramatically there. I don't want to go into the discussion there, but there is a bit of uncertainty, right?
Okay.
And the experimental data is also missing for fairly low temperatures, actually. There's no experimental data at these energies. We extrapolate.
Right. I mean, you mean the temperature around 5 to 10 Kelvin?
20, 30 degrees. We have more data at 1000. Yeah.
Yeah. Okay.
So if you notice the fits, actually, the fits will actually give you different values for different they will break it up at different temperature range. Okay, Drain's book is a very good reference too for this. How did I forget Drain's book? It's a more modern book written only in 2010 on interstellar medium. But I haven't used recombination coefficient from that book yet, but you can check that out also. So I hope I have answered your questions.
Yes,
But
yes,
this
yes.
is a different question. I suppose like if you had longer codes, we could compute it in
Mhm.
right here, and we could see what what uncertainties are of the computation of this rate. But yes, a point, good point you have made, and it should be good for all the other also who are listening to this, that we have uncertainty about various physical processes, even when it relates to hydrogen. We definitely have much more uncertainty
Mhm.
when it relates to atoms with more electrons than one. Like helium, we have more, and molecules and oxygen. I don't want to get into that, and I mean, it's a fact. Yeah. So hope I've answered your question.
Yes, yes. Thank you. Thank you.
Yeah.
Yeah.
So yeah, hi. I have a question.
Go on, please.
So same approach is being followed to study the recombination of helium also.
Yeah, okay, good question. Not in most codes, in most CMB codes, what is done is Sahanization formula is used to follow
Okay.
recombination of helium.
Okay.
And the reason is it doesn't really matter for the following reason, that helium recombination happens a little early,
Hmm.
right?
Yes.
So because it happens a little early, most of the action for prediction of CMB anisotropies happens around redshift of 1000.
Yeah.
Helium recombination mostly finishes by redshift of 1500 or 1800.
Okay.
So it doesn't play a very important role. So you don't have to take that into account very precisely, but it has been taken into account. So yes, your answer to your question is there are existing codes which deal with helium in exactly the same way as what I told you. Neutral singly ionized helium is very simple. Singly ionized helium physics is exactly the same as hydrogen, whatever I just described to you,
Yes.
right?
Yes.
Because it's a hydrogenic atom. Neutral
Yes.
helium is more complicated. It has some intermediate levels actually.
Okay.
It makes life more complicated. Okay. But the answer to your question, yes, it has been taken into account, and it does not play an important role in predicting CMB anisotropies. That's a correct answer.
Okay.
But you can look at papers by Kaluba. Kaluba would be one of the authors in many of those papers. He is one of those people who have done it in great detail. CHLUBA, Kaluba. Because I
CHLUB.
personally talked to him and he showed me some of the figures that they have produced by like studying recombination of neutral and single ionized helium more carefully.
Okay.
So I simply assume neutral helium has become full, that means neutral, by the time recombination of hydrogen starts.
Okay.
It's a good, I mean, it happens around 1500.
Okay. Okay.
But most codes, most CMB codes do not vary so much about CMB, helium recombination. They just use ionization formula. I'm not sure of class though. I mean, I know CMB fast very well. I mean, it's very simple. I mean, just use ionization formula and be done with it, because that doesn't play an important role at later stages, which are important for us. Hydrogen is more important. Yeah, go on. Are there any further questions? No? Then I'll go on and go to thermal history of the universe. Okay. So again, now you know why we were so careful about dealing with an ionized fraction as tiny as 10 power minus 4. It has to do with the thermal history of the universe. So, like I said, when we were discussing ionization history, I was dealing with a common temperature. I called it T. I didn't put a subscript CMB or matter underneath it, and now we're going to try to put it. The reason was that at high redshifts, the CMB and matter is at the same temperature. And again, it is important to say what this different forms of matter are. I said electrons, protons, and various things. And it'll be important now when we discuss what I'm going to discuss now. If matter radiation coupling, if you just study it below redshift of 10 power 4, above redshift of 10 power 4, it's a little more complicated. Below redshift of 10 power 4, the only processes which actually are responsible for the exchange of energy between electrons and photons. And by the way, I'll say electrons all the time. The reason is because photons exchange energy with electrons, not with protons. Compton scattering and inverse Compton scattering processes only happen with electrons. The protons, the energy exchange rate with protons is down by a factor of more than 10,000. So the point is they don't play a role. So what happens in Compton scattering or inverse Compton scattering is scattering happens of electrons gain or lose energy. But when electrons gain energy, they quickly share it on a time scale much shorter than the time scale of Compton inverse Compton scattering with the rest of the other charged species. Not just with charged species, in post-recombination universe, even with neutral species, those time scales are shorter. So let me just first discuss what the Compton scattering is, inverse and Compton inverse Compton scattering is. One should not even define it as two processes. One should simply call it Compton scattering, be done with it. But historically, we have dealt with these as two different processes. And they indeed have two different meanings. One is called Compton scattering, which is what we understand from our first course in quantum mechanics, that a photon comes and it hits an electron. And if you view the entire thing from the rest frame of the electron, electrons gain energy, photons lose energy. That is how we were taught Compton scattering when we were young. So I put a negative sign here. The change of energy of the photon is negative. But it's small because it is down by a factor of MEC square. So because we are dealing with a highly non-relativistic gas, remember MEC square is around 0.5 million electron volt. We are dealing with things which is around 1 electron volt. So we are way, way small. This exchange of energy is very, very tiny. Inverse Compton scattering is something we refer to, which is more a classical process. If you put electrons and photons at different temperatures, they exchange energy. And the rate of exchange of the energy, if you look at it in lab frame, because that's where the electrons are moving, that change is kT by MEC square. So one of them is h nu by MEC square, the other is kT. Where t, this t again, you'll say what t this is. Well, it depends on which way you are studying the process, from electron to photon or photon to electron. So that t could be either electron temperature or photon temperature. In the post-recombination universe, and now I will only study post-recombination universe. Let's look at the post-recombination universe. I already told you the universe is almost fully neutral. There are a smattering of electrons and protons, 1 part in 10 power 3, 1 part in 10 power 4. We discussed it at length. So you may wonder, how do photons interact with neutral atoms? They don't. I mean, this is called Rayleigh scattering. I mean, we study Rayleigh scattering all the time. And Rayleigh scattering cross-sections are much smaller than cross-sections of Compton scattering. And well, you can actually work that out. So again, I said, show that photon-atom interaction makes negligible contribution. So I leave that exercise to you. We can discuss it in case there are questions. Why this is negligible. So in post-recombination universe, radiation exchanges energy only with small fraction of electrons which are there in the system. Electrons gain or lose energy. When they gain or lose energy, the entire medium gains or loses energy, because they exchange energy with the rest of the medium, be it a proton or a neutral atom, on a time scale much shorter than the Compton scattering time scales. So that's the physics. These two processes. And it's pretty complicated studying it. And I have written down just one simple equation, which is the evolution of matter temperature. Okay, wait on. Yeah, now I'm good. So the matter temperature, the evolution of matter temperature, this is the equation 6, and we'll spend a little more time with equation 6. This is the change. Now I put Tm there, right? This is the matter temperature. It's not CMB temperature. Now I begin to distinguish between the two. There are actually two terms here. One is the first term, which is minus 2 A dot by A Tm. This comes from what is called adiabatic expansion. If you put gas in a box and let the box expand, just like the expansion of the universe, equally in all directions, then its temperature falls as 1 by A square, which we can actually show. And it does follow from the fact that the phase space distribution function actually remains conserved when the universe expands. And because the phase space distribution function of a non-relativistic gas is Maxwellian, so we are talking about mv square divided by kt, and so v falls roughly as 1 by a, so t falls as 1 by a square. So that's what explains the first term. So matter temperature, if the matter did not interact with anything, would fall as 1 over a square. It is the second term which is of greater interest to us. And this term has come from fairly complicated calculation, actually, both of these terms. They come from Compton and inverse Compton scattering. Both of these have contributed here, even though you might wonder where H crosses have all gone. They are somewhere. Point is, this term is proportional to Xe, and that's why we were bothered about Xe. Xe is the ionized fraction. if the ionized fraction was 0, suppose ionization formula was actually good and Xc dropped exponentially during recombination, then this second term would be completely negligible in the post-recombination era, and the temperature will begin to fall as 1 over a square. That's what we would find. And I've written it here. For X equal to 0, Tm falls as 1 over a square. But in fact, if you put numbers here, there is a radiation energy density, which is CMB. There is this Thomson scattering cross section, which is sigma T, the mass of the electron and the velocity of light. You would notice that, in fact, if I define 1 by Tc as this prefactor of the second term in equation 6, this actually is larger, the rate is larger than the expansion rate of the universe actually. And you can show it for yourself, and that Janki will show you. You have to put in these numbers, okay? Energy density of CMB, you have to put in that number, A, radiation constant, you should all know it. Sigma T, I have written the value, mass of electron C, you can compute it, and you can show that it is indeed larger than the expansion rate. So Xc is 1 part in 10 to the power 4, even then. For a while after the formation of neutral atoms at redshift of 1000, the medium, the thermal decoupling has not happened. So when at redshift of 1000 you finish the recombination process, the matter temperature is the same as CMB temperature, because the rate at which matter and CMB couple to each other is larger than the expansion rate of the universe. And this is an extremely important fact for what's going to follow during these lectures. And this is a number I would like you to compute for yourself. And this is a necessity, you should do it. And you get, from here you see the role of Xc, that even a tiny fraction of ionized electrons, free electrons, cause this coupling to be effective for a fair amount of period after recombination. And here I'm showing you one figure, thermal history. Now if you notice what I have plotted here, so I have plotted many things, so let me just take you through it. Not a great figure actually. There is this figure which is dot dashed. I'm sure all of you can see the dot dash figure, right? That is CMB. This is a figure, this is something that is falling as 1 over A. So left-hand side is temperature. So temperature of the medium as the redshift decreases falls as 1 over A of CMB. CMB temperature always falls as 1 over A because the distribution function of photons is conserved during expansion. And because it's proportional to h nu by kT, nu falls as 1 over A during expansion, so T must fall as 1 over A too. So CMB temperature always falls as 1 over A. There is the dashed curve, if you notice now. The dashed curve actually hugs the other curve. After redshift of 1000, you can see redshift of 1000 is here, almost like the extreme end of the right side, on the right side. These two curves are more or less the same, and they remain more or less the same, almost to a redshift of a few hundred. You can see that. Right? Couple of hundred, these curves are very close to each other when there is a decoupling. And the matter starts to fall. If you go to lower redshifts, you see that matter is falling as 1 over A square now. And that's precisely what, so it's a numerical solution of the equation I showed you in the last view graph. It's an important fact, I just wanted to mention it. That's why I showed you this figure. That on the right-hand side is the gene's mass I have plotted. And this is an indicative of when the first structures might form. So even though condition of formation of first structure is good, even at redshift 1000, they start to form much later, but the gene scale also slowly decreases through the period. But I'll not dwell on this point too much because I'm sure Tirth is going to have a much longer discussion on all of these issues with you. So the message here is thermal decoupling occurs way after recombination. Thermal decoupling is close to 200, redshift of 200, while the recombination happens at a redshift of 1000. And here is another nice plot that Janki sent me, which is like, again, it shows the impact of a different ionization history. And that's what we were discussing, an ionization history. Remember, we were discussing what different ionization histories will result in the thermal impact ionization history will have on thermal history. If you notice, and let's pay attention to this, this is CMB, the solid black line is CMB, right? The one at the top, the red line, has a residual fraction of 2 into 10 power minus 4, which is close to what we get by solving the equation, which is close to the correct number, right? But suppose by some process, and I don't know what that process is, right? And we'll come to that a little later in the third lecture, we'll discuss it. Suppose that residual ionization fell to 1 part in 10 power 5, 2 into 10 power 5. You notice what happens. You notice that the decoupling occurs much before redshift of 200, which is the preferred redshift for the cosmological parameters we know and the recombination coefficient that we know. Based on that, the decoupling should occur at redshift of 200. Here, the decoupling has happened more like redshift of 500. She has plotted yet another curve, which is for 2 into 10 power minus 6, and this is the blue curve. And you can see the blue curve, the decoupling, thermal decoupling occurs more or less at the same time as the recombination. And you can clearly see it. That these two almost coincide. At redshift of 1000, they begin to deviate from each other, diverge from each other. But what happens is, let's look at the final outcome of this. Let's look at redshift of 20. 20 is a redshift we are going to look at. Let's look at redshift of 10. At redshift of 10, the difference between a red curve and a blue curve is actually huge. One gives you a temperature of around 2 degrees. Another one gives you a temperature of around 0.2 degrees. It's a factor of 10. And this will have a bearing on when we discuss edges result. Day after, I think I'll come to it day after tomorrow. So I think I am more or less done for today, and I'll take question from here.
Hi Shiv. So as we are in this plot, can I ask a naive question?
Sure, go ahead. I can't hear you. Can you speak a little louder?
Oh yes, sure.
Yeah, go on.
Yeah. So two questions. So one, could you just repeat why the starting point is like starting values are same at redshift of 1000? And second thing is, what about the values below redshift of 10? Because we can have some observational constraints below redshift of 10 from like uniform background temperatures. There are other estimates from Lyman alpha or something. So what about like below redshift of 10?
Yeah, so you see, I have not plotted it below redshift of 10 because you see the ionization from Planck result, the reionization occurs around redshift of 8, right?
Right.
So unless you have a bound structure, so suppose you have a bound structure which has maintained the primitive state of the gas in some way, very unlikely to me, because once you form a bound structure, right, you will raise the temperature, right? So I don't believe at around redshift of 10 what you are saying might happen. I believe more like between 15 and 20.
Okay.
Because it is a little hard for me to believe that reionization occurs around redshift of 8. But at 10, the universe is could be almost unheated. It's possible. I'm not trying to rule it out. There are a whole range of models that one can actually construct. That thermal history is very different from ionization history. We ourselves have discussed some of those models, right? So possible. Your first, another question was related to the blue curve, is it? At redshift of 1000?
Right.
That's just an abstraction. I just wanted to show, right?
Okay.
It's just an abstraction. I just wanted to show what is possible if you change it completely, right?
Okay.
Because you see, at redshift of 1000, the recombination process just started, right?
Right.
So I think it is good to show it because you see, if somebody can come up with another model of recombination, right?
Right.
Then the truth might lie somewhere between these curves. You see, that's the point.
Okay.
We are dealing with a somewhat abstract model here, which is not backed by a physical process. because recombination coefficient cannot be so uncertain. And all the other physical quantities are also known to us. So blue or green curves, how they may arise is not known to us.
Okay.
But suppose we can come up with a model. I have thought a bit about it actually, but I don't want to discuss it here, right? Maybe you maybe somewhere between red and green, maybe,
Okay.
but it's an abstraction. So don't worry so much about an exact how it might arise.
Okay.
Just wanted to show the impact of ionization history on thermal history.
Okay. Thank you. Thank you.
Yeah, go on. More questions, please.
Hi, Shiv.
Yeah, please go on.
Yeah, so this amount of residual electron fraction around redshift 20, it will influence the formation of molecules, right? Molecules
That is
and
correct.
also magnetic field heating.
Yes,
Uh,
I can go
so,
back there. Yeah, here. Correct.
right. Yeah, so we need to know the precise number of residual electron fraction in order to calculate the amount of molecules, right?
That is actually the whole point is I have actually written papers on it of what happens when you change the ionized fraction on because I have worked with, I mean, this figure also is about magnetic field models. When you change the ionized fraction, so here you can see in these models I change the ionized fraction by orders of magnitude, right?
Right.
So molecular fraction actually it increases quite a lot.
Right.
You're absolutely right. So formation of molecular hydrogen, the history changes quite a lot based on which of these models you pick. Absolutely.
Yeah.
But what observation will I use to constrain that? I am not sure of. So unless one can detect a molecular line from one of those early objects, maybe it is something one should discuss in detail. I have not thought about it actually. Yes, I computed all this, but suppose molecular hydrogen fraction, its formation becomes earlier than usual, and that's what happens in all of these models. They start forming a
Right.
lot more in the intergalactic medium itself, unlike the usual case where the molecular hydrogen fraction is 1 part in 10 power 7 in the intergalactic medium, and the majority of them form after the bound structure is formed around redshift of 10. Here you can have more of them forming in the intergalactic medium itself. But I have not been able to, okay, so it's a fact which is interesting in its own right, but I have not been able to figure out any further implications of that. So that's a good thought. One should think about it. Absolutely. I mean,
Yeah,
this is the
because
time
this,
to think about. Go on.
if you believe in ages results, then one of the possibilities is that IgM is cold, and then this recombination rate will be enhanced at around 20 or so.
Yes.
This residual electron fraction will also be suppressed. Uh,
It should be suppressed actually.
yeah, and then it will influence all these things like molecular
Good.
formation, molecule formation, and this.
I believe that. Yeah, absolutely. One should study that. But I can tell you one thing.
Yeah.
Even if you suppress in the usual case, even if you suppress molecular hydrogen formation from say 10 power minus 7 to 10 power minus 9 by 2 orders of magnitude, it does not matter once you start forming the structure. Once you start a collapse process, molecular hydrogen
Right.
fraction will rise to around 1 part in 10 power 3 very quickly. It doesn't
Right.
matter what the initial state was.
Okay. Okay.
That I
Okay.
know actually, that I have studied. Okay.
Okay. Okay.
So it may not matter actually. But yes, absolutely. What happened? So you see, I'm looking for a probe in the intergalactic medium itself of molecular hydrogen. For instance, molecular hydrogen can block UV photons, you see.
Right.
So it can actually change the tomography of reionization process during cosmic dawn. I mean, it's possible. I'm just speculating. I haven't
Okay.
studied
Okay.
it. Okay.
Mhm.
So yes, it is possible as a probe. It is possible because the UV electrons can be blocked by molecular hydrogens. So yeah, but again, like I said, I haven't studied it. But good point. Yeah, it changes.
Okay.
Any
Thank
further
you.
questions? Go on.
Shiv?
Yeah, please go on.
So this fall off in the ionization fraction, so we would not see the effect of reionization around redshift 10. I mean, in this solid line, would we not see some it going up? Or
Yeah, you will. I haven't plotted it. I'm sorry, I haven't plotted it. This is a paper from 2005. Okay.
And how this curve actually would fall off also depends on when reionization started. I mean, when was the epoch of reionization? Does it depend on that?
Well, it will. See, like you said, epoch of reionization will actually change the history. After a redshift of maybe 12 or so, it will start to rise and reach 1, right?
Yes.
But not at earlier times. It won't change at redshift of 50. Why should it change redshift of 50? Well, okay, partially ionized maybe. Look, I have actually shown a set of models which can occur from early reionization, from early solid reionization, slow process. Okay.
Yeah.
So yes, all of these models, very difficult to rule out any of these models. I have studied CMB anisotropics for some of these models, even though I never published. It's very difficult to tell. So there is a fair amount of uncertainty about ionized fraction. So in fact, it's not a bad curve because you can say that when ionized fraction changes at redshift 20 from roughly few time in 10 power 4 to almost 0.01, I have no independent measure of it except edges result. Edges results does constrain it because a different ionization history would mean heating also, right? And edges result actually constrains heating quite strongly. So yeah, it will change, but again, very difficult to tell the difference between them, these curves. So point up to 0.1 is not very well constrained because you see CMB does not interact so much. But if you were to go to 0.5, then it will make a difference. But again, Planck result will rule that out. I can't go to ionized fraction of 0.5 at redshift of 20. No way. Because I'm reaching 1 around 8, right? So again, a whole range of models possible, absolutely, within this framework. Yeah, reionization, I have another plot with me where reionization is there, but I haven't shown it. It'll rise suddenly. I mean, depends on the model you have of reionization. And then it'll remain close to 1.
Thanks.
Yes, please go on. Any further question? I've run out of time also. So maybe one last question.
I think there are no further questions.
Okay.
So you can stop here.
So I can stop here and urge all the participants to actually, whatever I said about computing things, please compute those things. Okay. Anyway, Janki is there. So she's anyway going to hold a tutorial session. So it's important that you compute those things yourself to get a sense of what I was talking about.
Yeah, hello, I want to ask something. So
What?
is there can you suggest some reference for reading this post recombination part? So we know Dorelson is good for pre-recombination.
No, not Dorelson actually.
Yeah, but for post.
I think you discuss that with Janki.
Okay. Sure.
I do not have a single reference for Peebles' book is a good reference actually.
Okay.
For what I discussed today, recombination and thermal history, the book of Peebles for physical processes is good. But you may want more recent references also. Right?
Yeah.
I cannot. Janki, maybe you can actually think of some review. I mean, I think there are some reviews about 2010 that might give you a good sense of this. I mean,
Yes, okay. I will compile and put them in.
sure. So please do that. Okay. So you'll get the answer there.
Sure.
Okay.
Thank you.
Yeah.
So I think I'll stop now.
Okay, then stop sharing, Shiv.
Stop sharing. Yeah.
Yeah. Thanks, Shiv.
Thanks.